All right, so welcome everyone. Today we have Nima Rasekh, who's going to tell us about univalence maxim for category theory.
All right. Well, before I start, let me make a couple of comments. First of all, of course, let me thank Maru for inviting me. And thanks you all for attending my talk, wherever you are. And the talk is slightly unusual because it's not like a problem and theorem solution kind of talk. It's somewhat more of a maybe foundation kind of perspective type of talk. And I'm trying this for the first time with a homotopy theory audience. So I don't know how it will work out. So in particular, this means that I don't really have anywhere to get to. And if you want to ask questions, please do. The time is 60 minutes, right? Just to make sure.
So maybe 50, 55 plus some questions.
55%. Okay, good enough. Cool. And so if I happen to say anything new that I have done, everything I say is joint work with Benedict Ahrens, Paige North, and Niels van der Weide. So let me also make that comment. All right. So I wrote in the abstract that I will take for granted that you know what a category is, but nothing else. So I will take for granted that you know what a category is. I hope that's fine for a topology seminar. And so I will just also take for granted that categories are important and you like them and they appear in papers you have read or papers you're writing or whatever. And sometimes the key observation and a key point of this talk is that categories and their generalizations, so in general categorical structures, appear up to many different notions of equivalences and that we care about, and that kind of causes some confusion. And what we would like to see is, okay, can we kind of clarify this? And this cannot be done that easily in classical foundations. You have to kind of use contexts to get through that. And I want to kind of tell a story how if you look at things from a univalent perspective, then that becomes easier. And I will say what I mean by that. So that's kind of most of the talk. All right. So equivalences of categories. So there's at least two types of equivalences of categories that you naturally encounter in the math literature. And that's isomorphisms and equivalences, right? And so they both exist. There are examples of those. I will just move on and just as like a reminder. In particular, they have different properties. For example, you will have the fact that isomorphic categories have bijective sets of objects, whereas for equivalent ones, it's not true. On the other hand, often equivalences are enough to kind of transfer important categorical properties, right? So completeness, presentability, and so on. And so you kind of have a choice of two notions of equivalences when you're working with categories, and you kind of have to choose depending on what your aim is. So let me make one fun comment. So a lot of places you will say something like let S be the set of objects of the category C. But in some sense, if we are thinking of a category just in terms of an equivalence class, then this would not be a well-defined sentence because the set of objects of an equivalence class of categories does not exist. So it's a common thing where papers will treat categories up to equivalence, but we'll also talk about the set of objects of the category. And so these two technically have an issue where you have to be somewhat precise. I will not assume that you know what a true category is, but I assume this is something familiar. If I was in a room, I would say raise hands if you know, but I'm not, so I will not do that. But let me just mention, so some types of categories have naturally two morphisms between them, one morphisms. And the stereotypical examples that people mention always are natural transformations for functors or morphisms of bimodules. And we think of bimodules themselves as morphisms between rings or morphisms of relations if you want to. And in that case, then you can define a two category or more generally a bicategory. And this is one of those places where having slides is super nice because I would never write out all of these conditions. But having slides, I can just throw them at you and show them once and say I've done this. So a bicategory kind of has data, zero objects, one morphism and two morphisms, then some compositions and identity, but then somewhat interestingly, all of these things are up to weak conditions. So the composition is only given up to some associator and unitor. And then you need to satisfy some coherences that I've not added because that would get too long. And so in a bicategory, I can look at even more equivalences than what I could do in a category. right? So I'm not, so before I do that, let me mention that a two category is a bi-category in which the Unitarian associated is trivial. And so very precisely now I can actually form the two category of categories, functors, and natural transformations. But for the other two, I would only get bi-categories because, well, in the case of bi-modules, the composition would be tensor product, which is not strictly associative. And in the case of sets, it would be pullback, which is also not strictly associative. All right, so I can look at various classes of equivalences for two categories and bi-categories. So there's still isomorphisms. And then there's this notion of kind of bi-equivalence on the other end of the spectrum, which is like the weakest one. But then I have like some kind of variance in between where I can say, okay, like two categories are equivalent if the underlying one categories are equivalent, and I have bijection on two morphisms or something like this. Or I can look at a bijection on objects, which is a local equivalence, right? So there's some variation that like is that allows me to give different notes of equivalence. And again, they have different properties, so it kind of matters which one I care about when I'm trying to do something, right? So like a simple observation is, so if you take like this map here, so here I'm defining this thing called the free adjoint equivalence, which I will not specify because it's a lot of data. But the key fact is it has like two objects and has many one morphisms, infinitely many in fact. And it is a bi-equivalent to the point. That's the fact. And so these two don't have the same set of objects, they don't have the same set of one morphisms, but they're still bi-equivalent. And so you don't preserve these kind of properties, right? If you're studying a bi-category up to bi-equivalence. So let me move on. Look at a third kind of categorical structure, namely a double category. And so a double category is kind of come up if I want to look at the category, but I happen to have two types of morphisms and I don't want to choose. Like I don't want to say I have an object and two reasonable notions of one morphisms and I want to pick one of them and define a category. I want to keep both of them around for whatever reason. And there's now a variety of reasons in the like math and applied math and even in the computer science literature where like people look at double categories and use them to do like fun math. And so in that case, and like we keep track of both the one morphisms and kind of add a notion of square to kind of, well, do what we want to do. And so a more precise notion of a double category is given by, well, either we can say a category object inside a category of categories. But more explicitly, we have like objects. We have two types of morphisms, which we call horizontal and vertical. We have squares, which become in between the horizontal and vertical morphisms. And then we have like a ton of compositions, identities, unitality, associativity, and so on. And like this kind of list is very compact. So to kind of give a more diagrammatic idea of a double category, we can kind of capture it like this, right? We have the objects in the top left corner, then we have the morphisms, the horizontal and vertical ones, then the squares, and then the various compositions. And so unsurprisingly, we already saw with two categories, we had way more equivalences than with categories. And with double categories, we should have even more. And before that, let me mention there's also, again, a strictness issue. So there's not just one notion of double category, and we can kind of choose how strict our notion of double category should be, and there should at least be three, where I can say either the composition is strict in both directions, or it's strict in one direction, weak in the other, which is called a pseudo double category in the literature. And then like there's one which should be weak in both, and it doesn't really have a name as far as I can tell. That is kind of agreed upon in the literature. So you can call it like a doubly weak double category, or if this is too many doubles, you can just call it a weak double category. I think they're both reasonable names. And so now, this here is like a selected list of equivalences that I could find in the literature. So this is not exhaustive. So there's again the isomorphism, which is kind of like one end, if everything is very strict. And then there's this thing called a gregarious equivalence, which is kind of the other end. And so it's like a symmetric kind of very weak kind of equivalence for double categories. And then there's at least like four in between, right? Which kind of like where you choose a direction and then you kind of impose in which direction you have some kind of equivalences of categories or bi-categories. So we'll come back to this a little bit later on. And if you put this all together, you see there's some kind of increasing function where with the complexity of the categorical structure, you get like more and more equivalences. And so presumably you would expect if there was like a next column, like, I don't know, triple categories or tri-categories or whatever, this list should get longer and, well, harder to keep track of. So the whole point of this first part is to convince you that when I look at categories, I also kind of implicitly at least also look at some notion of equivalence that comes along with it that I care about. And in the case of literally categories themselves, it's easy to ignore it because there's only two choices. And well, equivalences are strictly weaker. So it's easy to say, okay, whatever, I just keep track of, I just choose equivalence all the time, unless the couple occasions where I need isomorphisms, and it's fine. But things degenerate quite significantly very fast, right? So in the case of double categories, these 6 ones are not all comparable to each other, right? So there's no like nice linear order between them. They have like different relationships. So it starts to get tricky. So what can we do? Right? Whenever we have a problem, we want a solution. That's the way of math. And the solution, the first kind of solution I want to come up with as a category theorist is to just go higher in the category ladder and add more higher categories to solve the lower categorical problems, which then presumably we create higher categorical problems which you have to solve by going even higher. So I don't know. So let me just give you an idea. So a KN category will be some sort of idea or concept. So it's not a definition a priori of something which should model having objects, having morphisms up to level K, and having some kind of invertibility condition for everything above, everything above, no, morphisms, yes, everything from N to K has to be an equivalence. And so there's various ways of making this into an actual precise definition. And we don't need all of KN categories. So let me give you some sense of the ones we need. So a 1-1 category is a precise ordinary category in the way we've seen before. 2-2 categories should be like bi-categories. 2-1 categories should be like bi-categories in which all two morphisms are invertible. And this is a topology seminar, so presumably infinity 1 categories are the ones most familiar to people. So these are like quasi-categories, quasi-zero spaces, and so on. And so what I can now do is look at a category, but think of, okay, what kind of higher category is it sitting in? And so concretely, what I can do is I can define two, higher categories of categories in which one of the higher ones is not really that high. So I can define the 1-1 category of categories, where I just have categories and functors. It's easy. And now I can define the 2-1 category of categories, where I have categories, functors, and natural isomorphisms. All right. And now I can ask myself, what does it mean to be an equivalence inside that higher category I've chosen? And so in the 1-1 category, it will be precisely isomorphisms. And in the 2-1, it will be equivalences. So very nice. I can like choose a categorical level and then kind of very precisely specify the kind of equivalence I want by choosing the categorical level. All right. Of course, this needs to have some issues, or else the talk will be over on slide 20. And so let me mention a couple ones that come to mind. The first one is we still have to then always specify what the context is. Like it doesn't actually like kind of absolve us of this responsibility when working with stuff. And something even worse, there's no correspondence. Like in this one particular case, there's a very nice correspondence between like levels and equivalence types. But for example, for double categories, this is not true. And so you can have 2-1 categories of double categories. And depending on how you pick the natural transformations, you will get different kind of equivalences. So it's not even enough to just say, oh, I want a double category, but in the 2-1 categorical sense, that would not suffice to specify what you want. Another issue that comes up is that adding higher structure has a motivation beyond the equivalence type of what you're looking at. Right. So for example, here's a very crude lemma that like, I don't know, a simple exercise for maybe a student starting to learn category theory. If two categories are isomorphic, then presumably natural isomorphisms out of one and the other should be bijective, something like this. And here, if you look, the isomorphism symbol suggests these are objects in a 1-1 category. But trying to work with natural isomorphism suggests some sort of 2-2 or 2-1 category. So there's kind of a divergence between, okay, what's the category level we actually want? That's not nice. All right, so then let me wrap things up for this section. So what did we discuss? We basically saw stuff that most of you probably already knew and just like focused more attention on it. Namely, categories are interesting. They come in various shapes and forms, and they come with many equivalence types, and that causes some confusion. And we can try to kind of avoid this issue by adding some high categorical context, but this kind of causes its own confusion because, well, high categories kind of are hard. All right, before I move on, are there any questions, comments? So this is like the motivational part.
Could I ask, I just want to take way back at that slide, I don't know what, that you mentioned the category of sets and you put down the morphisms as relations. And indeed, if you have mappings of sets, they are relations, but not all mappings of, not all relations are mappings of sets. And what one morphisms did you mean there? Did you mean a category where the morphisms are indeed all relations on the pair of sets?
Well, I mean, I guess what they really had in mind was spans, but I guess I wrote relations because it might be easy.
Oh, yeah. Okay, good. Thank you. Yes.
So, yeah, I should have just been spans. I don't know. It sounded like a more threatening word, so I avoided it. But no, it makes no sense. Okay, does that answer your question?
Yes, thank you.
Okay.
Subset of a square, whereas a span is a subset of a product.
Any other question? I cannot see all of you, like I said, because the camera doesn't move along. So if you have questions, please just like yell out so I can at least hear you. All right. So can you repeat this?
You want the camera to move.
You asked earlier to freeze the camera, so that's what I did, but I can unfreeze it if you prefer that.
I mean, like I said, if as long as you ask questions whenever you have one, it's fine. I mean, I can hear you. Like I said, I cannot see everybody at the same time. So, all right. So then, let me move on.
And we'll interrupt if we have any questions.
Good. And so, move on to the world of univalent foundations. So, univalent foundations is a new foundations for mathematics. It's well, it relies on the univalence principle, which aims to kind of have a stronger notion of identity. So I'll explain what I mean by that. And well, the point that I want to make in this talk is that using this stronger notion of identity in univalent foundations kind of helps clarify categorical structures and really kind of make the equivalence type part of its structure in a way that was kind of already understood in homotopy theory, but this makes it really explicit and part of the foundation. That's kind of how I see it. All right, so before I can say something about univalent foundations, it's helpful to say stuff about type theory. And so type theory, I think, in the minds of many people is associated with computers and computer science kind of stuff, but it really doesn't have to, right? There's nothing fundamental about this. And if you've never, I've never really worked with type theory, I kind of added this slogan that like Mike Schumann told me like many years ago, is like doing type theory is like doing category theory and zooming in so much that one forgets that one's in a category. So one kind of remembers some parts of the category, but not that that there's outside, so like a global something of objects or Hom sets. All of this is gone. We just literally with the objects themselves. And so in type theory, there are types, there's terms, and there's type constructors. And the type constructors tell us what we can do with the types and terms. And the analogy in category theory is, roughly speaking, there's objects, there's morphisms, and there's universal properties. And just to like clarify this a lot, like type theory goes back to ideas of Russell, and that's like from 1908. So it's nothing to do with computers a priori. So let me give you a sense for how types behave and like what kind of constructors we have. So there's the obvious ones like the unit type and empty type, which basically you should think of as initial and terminal object. Then there's things like a product type and a function type. So a product type is a product. The function type, just to clarify, you should not think of like a hom set or hom object. It should really be like a Cartesian closure, right? So because for any two types, it has to be a new type. So in the analogy, it would be another object in the category. So that's exactly what Cartesian closed would mean. The confusing part about type theory is to remember that, okay, not only are we internalizing the kind of usual constructions that we are used to from category theory, we're also internalizing everything that we use to reason about mathematics. So there's nothing outside of type theory. Right? It's really like strongly imposed in some sense. So let's look at some examples of this. And a key example that plays an important role in this talk is the identity type. So if I have a type X and I have two terms, I have a new type, which, well, is the identity type between those two. And that is, again, it's a type itself. So it's not something outside the kind of mathematical realm. And this is very different from, let's say, set theory, where like the sentence S equal T is not a set. It's just it's like a sentence or it's a formula, depending on how the variables are. So here it is, again, a type inside a type theory. And now you can ask yourself, okay, what would it mean for two terms to be equal? And well, two terms are equal if the type of equalities has a term. So it's like not just the empty type. Then I can do the same thing. So here, let me, so I made a mistake in my order because I want to also have a universe type, and I used my universe type the slide before. So let me come back to this. So I can have, let me say this first and then come back to this. Yeah, so I kind of changed the order of these slides. Sorry about that. So there's also a universe type. So a universe type kind of tries to get around the fact that without it, I don't have any sense of, I cannot say anything about all types at once because there's nothing outside. So I add this new type and I say a term in this is precisely a type. And of course, this is very paradoxical because then U cannot be a term in itself. So the same way that like we need to like kind of have a set of all sets, we cannot have a type of all types. And you have to kind of address this in some ways, but I will completely ignore this. So there is just a type U where something in U is the type. And now coming back to this, if I want to ask myself if two types are equal, how can I determine this? Well, I form the identity type of them as terms in the universe, and then ask myself if this is empty or not. And a priori, the only identity I have is the so-called reflexivity, right? So it's the one that says everything is equal to itself. But that's all I know, right? There's a priori no other identity I have in a type theory. So if I want more, I have to kind of add some axioms or conditions or something. Yeah, let me remark again. So this is like really important. Like this X equals Y is a type, right? It's not anything outside, right? It lives in with all other like types and objects and whatever you're thinking of right next to them. There's nothing separate from it. There's nothing separate from types. Okay, so I already told you what the universe is. We can move on. So I want to kind of be able to start from one type and build more structure on top of it. And this will become very relevant very soon when we want to kind of use a more logical arguments about types. And that's done via what is called a dependent type. So a dependent type sounds like a very fancy name, but a priori it's just a function into the universe. That's all. And what it's saying is that, okay, if I think of into the sets, like U should be some sort of the set of all small sets or something like this. And then this is just saying I have a set index collection of sets. Something like that, but in a type theory world. And now what I can do is I can do two very fancy constructions, which play an important role in type theory, namely the sigma type and pi type. And the sigma type is in some sense like the, I don't know, the union, but over the type I've chosen, whereas the pi type is more like the sections of this. So a term in a sigma type is a pair, but where the second component, notice if I want to determine where the second component lives, I have to look first at the first component, and that just determines where I can find the second term. A pi type is kind of similar, but now I have a function, and the value of the function is always determined by my dependent type. So it's giving me the notion of a section, but internal type theory. So let me summarize this all. So we saw unit type, empty type, product type, functions, universes, identities. Then we have dependent types, and with dependent types, you can do sigma and pi types. And for example, in the world of set theory, if you want to kind of have a sense how they correspond, there would be exactly the usual notions, where like a dependent type corresponds to a function. So here, the one kind of fun thing, confusing thing, maybe the notion here is that the identity type corresponds to a diagonal. And why does it do that? Well, because in a set, two things are equal. Well, if they're exactly equal, and then there's only one witness for the equality. And that's what the diagonal is doing. So the diagonal map exactly has its image inside x times x, well, pairs where the two components are equal. So that's what they're capturing. So again, like the identity needs to be something inside, so it needs to be a set, and it's exactly the diagonal. All right. Now, using these kind of like constructions, we can start to reason within inside a type theory. So for example, I can like now define this type, and I can say, okay, what does it mean to be a term here? So what would a term here be? So I start with some m maybe and say m is in mag. And then I look at, okay, what's the rule? It says I have a sigma type of some dependent type. And so let me go back. What do we saw? A sigma type is some kind of pair. So all right, what I want is a pair. So m then should be a pair of some x, and then some second part of the sigma type dependent on the first. And in this case, it's exactly a product. So there you go. I mean, this looks like a very trivial unwinding, but of course, because the example is not like the most complicated one. But building on such simple examples, we can essentially internalize a lot of mathematics into this type theory setting. And so I can keep going, right? I define a magma by the sigma type. Now I want, let's say, an associative magma. So what should that be? It should be a magma, and then it should have the additional data that, like, I don't know, there's not associativity conditions. And that is exactly captured by a pi type because that's the section condition, right? It's exactly telling me that, okay, I have my let's say x, I have my product, and then additionally, I have a section into this equality, which is telling me that, okay, like, well, the associativity condition. And similarly, I can like define, well, I can say a commutativity condition. And now I can ask myself, okay, how do I prove stuff inside type theory? Well, there's sometimes rules that tell me that, okay, if I want to prove, let's say, an if statement, what I do is I construct a function, essentially. For example, if I want to prove a statement like every commutative associative magma induces an associative magma, what I need to do is I need to construct a function. So I really just need to construct a function of this type. And in this case, it's super easy. I just have pi1, the projection. Like I forget the commutativity structure. But so in general, I can just keep going like this. I kind of construct mathematical structures using a combination of pi, sigma, and identity. And then I write statements and then start proving them by constructing terms. That's the whole game, a priori. Okay, let's say you're kind of like not convinced and say, who cares? And I've been doing set theory for like 45 years. I think it has been completely fine. And why should I ever look at a type theory? And in some sense, the whole point is because I've internalized my notion of identity, I can now ask myself, okay, how is it supposed to behave? Like, what are the rules that my identity should satisfy? And coming from a classical background, the first one can guess is the following, that, and let me like unwind this, what this is basically saying is that if I have like for all x, for all types x, and then xy terms in x, I have p equals q. I forgot one step. And p and q are two identities, then I need to have p equals q. All right. And this is essentially saying that if I have two witnesses that two terms are equal, those two witnesses need to be equal themselves. So there's no additional structure for being equal. Right? And this is roughly how we think of the equality symbol in set theory, right? So we have two sets or two whatever structures. We say they are equal, but being equal is not kind of an additional structure or property to care about. It's just something that we either have or not. And so this cannot be deduced from the type constructors that we have introduced up until now. There's no reason that this has to be true, but you can always assume things to be true. There's nothing that speaks against that. And that's what's called the uniqueness of identity proofs. So it's aptly named because that's exactly what is imposing. And if you do that, then yes, then roughly speaking, in a type theory, we have in a setting where our equality behaves roughly the way we imagine it does in, well, classical mathematics. But the point is that this is not the only thing we can do, right? So we can do something else. And so for that, I have to first tell you what the type of equivalences are. So this is roughly what you imagine an equivalence should be. An equivalence should be some map which has a left and right inverse. And so there you go. I'm saying that the type of equivalences is given by a collection of three maps so that the first two and the second two compose the identity. And if I think of this as sets, this will exactly be isomorphisms, but a priori, if I think of types as something else, this can be like manifest in other ways. And now, do I have examples of equivalences? Well, yes, I do. Every identity is an equivalence. This is not like obvious per se. One has to do some work to observe that whenever I have a path, I can construct some kind of inverse path that composes the identity. So this is like one of those. I already used the word path, so I'm kind of cheating. But the point is that if I have, it's actually true that if I have like an identity, gamma, then I can really construct always some kind of inverse identity in the other direction. And what it is saying is this is basically the symmetric condition for the identity relation, right? We think of like, if you think of the equality symbol as a relation, then it should in particular be symmetric, and this is what this is saying. And so there's this univalence axiom, which says that the identities are exactly captured by the equivalences. So it's not only saying that there is, well, either one equivalence or none. It's saying there are as many identities as there are equivalences between two types. That can be a lot, right? So depending on what kind of types you're working with, you can have a lot of identities now. And so in fact, you can now use this additional axiom to prove a lot of new things about your types that like are very homotopical in nature, right? So this is like stuff that is familiar to us. So for example, we can say, okay, a type is a -1 truncated or a proposition if the following holds, right? So I'm saying here, if this is true, that for any two terms, they're equal, then I say it's -1 truncated. And then I can keep going, right? I can say, okay, it's 0 truncated or a set if it is true that for any two like identities, they have to be equal. So this is very reminiscent of truncation levels in homotopy theory. And so in some sense, we can say, when working with univalent type theories, we're kind of like updating the original slogan we had is kind of similar to working in some sort of higher category, but then zooming in so much that we forget that we were in a higher category. We just see the objects and we see how they interact with each other. And that's it. We don't know what the mapping space is. We don't know what the space of all objects is. We don't know any of this. And maybe to add somewhat more explicit model that you can think of is we can think of types as kind of being Kahn complexes or homotopy types, or I work at the Max Planck Institute, so I'm contractually obligated to mention anima as a way of saying Kahn complexes or homotopy types. And we can think of them as like modeling univalent type theories, where more or less we have exactly the same type constructors we had before. So a product type is still a product type. There's nothing interesting about that. But some of the ones that change is, so a dependent type, now we often think of as a Kahn vibration, because the dependence should really be depending on the paths and the higher cells that are in the Kahn vibration, which didn't exist in a set. And the identity type now is precisely given by a path vibration, which is saying that, well, the equality between two terms is given by the equivalences in them, right? So Why does a path vibration make sense? Because if you have a path vibration sitting over this, and we have, let's say we pick this as a terminal, and if I look at this, then this is exactly saying I have paths from A to B. And this is what I want to think of as being the identity type of A and B inside the type A. So here, A and B are two terms. There you go. So this exactly fits now the description we had. It's not obvious now to see that. Yeah, it's not completely obvious to see that now all the univalence conditions stuff are hold, but they do. And so in particular, then n-truncatedness is exactly n-truncatedness in the usual sense of how we use it in topology. All right, so let me summarize the type theory portion. So type theory is a foundation of mathematics. It can have something to do with computers, but it doesn't have to. The key factor about type theory is that it internalizes everything. So there's nothing outside of type theory that we can see. And this in particular applies to the identity. And the identity can now manifest in ways that we used to, so via UIP. But it can also manifest in ways we are not used to. Or maybe we are actually used to secretly as homotopy but not explicitly used to, at least, via the univalence axiom. And now the goal is leverage this richer, stronger identity that comes from a univalent foundation when looking at categories. All right, I'm now want to go back to kind of the issue that I raised in the last section, and go back to categories. So maybe this is a good time to stop and see if there's any questions about type theory, about univalence, about anything else. Okay, I'm not hearing anything. So there's two scenarios. Either I'm very clear or you're all asleep. So I very much hope it's the first one. All right. So let me remind you what the aim was. So in the first section, we saw there's tons of categorical structures. We focused on 3 categories, double categories, 2 categories. And there are too many equivalences to keep track of. So it gets exhausting. So what can we do about this? And the claim now is univalence can help. So I did all of this stuff in the previous section, so I can like do this slide, and like this should make sense now somewhat. So a category in type theory can now be defined this way. But I start with a sigma type, where the sigma type says, okay, I have like pairs. So now I have exactly what I usually think of as in a category, right? I have a type of objects, I have a type of morphisms, I have a type of composition, so my multiplication, I have an identity, and I have all the standard axioms telling me that, well, it's unital and associative. The only one I kind of have to mention here more explicitly is that because I'm in a univalent setting, a type is generally not a set, but I really want to have a category and not some sort of, let's say, enriched or higher category. So I'm imposing a set condition on my morphism types. Like I want to guarantee that everything is a set. So now this roughly looks how categories look like in classical math. There's no fundamental difference. But I have now more leeway to define new stuff. And before I do that, I want to come back to my case of Kant complexes and use my kind of intuition about Kant complexes to make clear what I want to do. So this definition, I mean, if you think about it, it's kind of like if I think of this as sitting inside spaces, I can think of categories as this is like an internal category inside types. So I have like an O here, maybe I have M, and then like these 2 maps here telling me that I have 2 maps to O and so on. And so I kind of like forming some kind of like simplicial object. And maybe we do know, or maybe not, that we can look at categories internal to Kant complexes as this notion of a Siegel space, which is a simplicial space that satisfies well the Siegel condition that gives me some kind of nice categorical structure. And in the Siegel space formalism, the mapping space is precisely given by, well, W1. That's kind of how things work. And if I add the condition that the mapping space, so this kind of source target map is zero truncated, then I actually don't need everything about a Siegel space. I really only need levels 0, 1, 2, and 3. right? I need the objects, I need morphisms, I need two compositions, and I need three compositions, and then I'm done. That gives me all the structure of a category. So, in other words, I should really think of this definition as secretly being some sort of single object in types where my morphisms are zero truncated, just sets. So that's kind of like a good way to think about this category when I'm working in a univalent setting. And so now here's a question I can ask. When are the equivalences of two single spaces precisely the isomorphisms in just a very classical setting? Or even more generally, when are equivalences between two Kant complexes isomorphisms? Are there any answers? This is like a classical topological question. Wait, there are no answers to this? Is the question unclear, or is it harder than I thought? No, it can't be harder. So it's probably unclear. All right, then I will answer it myself. But I think you probably already knew the answer. So
I have an
right?
answer. The answer to both questions is rarely.
Indeed, but what is the condition that this rare condition I have on the Kant complex that will guarantee to me that an equivalence is an isomorphism? There is a condition, and namely it is if the Kant complex comes from a set, right? If the Kant complex is like constant, if I think of the Kant complex as literally as a simplicial set, if it is constant, if it's a set, then it is true that an equivalence is precisely an isomorphism, because I mean that's just what it is. And so in other words, then if I look at my answer to question B and then apply it to question A, what I should think of is, okay, the equivalences between two single spaces are precisely the isomorphisms if this level-wise just a set. Like it's a simplicial, instead of being a simplicial space, it's like a simplicial set. And so this turns out to work also in like the univalent setting. So I can define this funny word as a set category and say a set category is a category where I also assume that the type of objects is a set. Notice this will also imply that the type of morphisms is a set, right? So because coming back here, because if I assume that this is a set, I'm assuming the map in between is a set, so W1 will also be a set. So it's like we'll transfer up. So in particular, then the whole level, everything will be a set if you assume that the objects are a set. And so yeah, in spaces, those are exactly the single sets. And then one can really explicitly prove now that if I take this notion of category, so the set categories, then the identities are precisely the isomorphisms. So in other words, if I take two such things inside cat set, then it is true that C equals D in this thing is the same thing as iso C. So that's what I wanted. There you go. So now the next question is, I've been given two single spaces, and I want to know that the equivalences of the single spaces are exactly given by the categorical equivalences. So this is something that some of you in the audience very much know the answer, but some of you might not know. And there's a precise condition we can impose on single spaces, and it's called the completeness condition. And I will not tell you what it is because that would digress too much, but it's kind of an internal analog to the univalence condition, and this goes back to work of Rasekh. And so this completeness condition can be also imposed on categories. And so what we can define then is univalent category, and this exact same condition holds, namely identities in the type of univalent categories are exactly the equivalences. So this suggests that the answer was kind of known, and what we're doing is kind of just setting a foundation for something that was already understood. And I think this is really true. right? I mean, basically what's going on is that I can take here the 1-1 category of categories, and here I can take the 2-1 category of categories. And I can take the very kind of generic nerve, where I literally just do the usual nerve of categories, and like as a discrete simple space, or I can do the so-called fancy Rasekh nerve, and those both will be embeddings. And so I can kind of look inside complete single spaces, which categories am I picking out via the usual nerve, via the kind of the strict nerve, and which categories am I picking out when I do this kind of Rasekh nerve, and I give them kind of explicit names in this univalent setting. And the cool fact is now I can keep doing this, and I can keep doing this with like lots of other structures. So yeah, let me summarize then. I have set categories in this setting, but I also have univalent categories, and they have exactly the identities I would like, depending on what I'm trying to do. And so I can keep doing this with 2 categories. So I'm supposed to finish at, I think, 20, because I said 50 minutes. So I will skip the 2 category part and get to the double category part, which is like somewhat more fun. Here. So for double categories, let me mention one thing. So again, let me remind what a double category is. I have the structure of objects. I have 2 types of one-morphisms. I have squares and I have various compositions. And I want to focus on one specific case, namely the case of a horizontal equivalence. So, or vertical equivalence, I guess. I should have changed this probably. Let's see. So a double functor is a horizontal. Yes, this should be a vertical. Sorry, this is a typo. Yes. So a double functor is a vertical equivalence if what is true is that I can restrict to this category and restrict to this category, and I have an equivalence restricted to these 2 separate categories. When I like take my double functor and restrict to functors on these underlying categories. And now I can ask myself, okay, what kind of condition should I impose in this kind of univalent setting so that the identities are precisely the vertical equivalences? And what I've learned from category theory is that, okay, what I should do is I should like say, okay, this category should be univalent, and then this category should be univalent, and then this should do the trick. But what I notice is when I do this, then the objects and horizontal morphisms will not be a category anymore, in the sense that they are neither a set category nor a univalent category. And because I cannot have my objects be set, because the objects are already determined by the vertical morphisms. And also I cannot have univalence condition in the other direction, because that's not what I want. And so the implication is that I kind of have to add some kind of further structure and move from a strict double category into one which is a pseudo double category. So this is kind of like a fun realization that sometimes when you want to impose appropriate invariance on like a chosen equivalence, you have to also adjust the categorical structure along with it. Right, so this so concretely then, if you want the identities to be vertical equivalences, you can define a univalent pseudo double category, where like now the statement would be that in this direction the composition is only weak, and there's nothing else I can do about this. A fun fact. All right, so I want to keep going with this because it gets boring. But here's kind of like the kind of diagram you can get where like you think of, okay, I pick my categorical structure, like a double categorical structure of interest with an appropriate weakness level. Then I pick invariance, an equivalence type I'm interested in. And then I can kind of construct in a univalent setting an exact categorical structure that has that equivalence type. And so here in this diagram, kind of a dashed arrow would mean that, okay, just at the level of like ignoring the invariance, I would have some kind of embedding, whereas a full arrow would mean that it preserves both the structure and the invariance. So there's kind of like an interesting connections to get between these different notions. And so then finally we get to, well, what we call the univalence maxim for categorical structures, which is basically just saying that I can really do this for every arbitrary categorical structure I have in mind. That whenever I have some kind of categorical notion, I have an equivalence, I can construct some appropriate definition in this univalent setting that has the right kind of identities, exactly in the way I expect. And so this is like an example of the ones you get, but presumably there's no reason that this would not work for anything else that you have in mind. I'm mostly out of time. So let me like make one last comment and then end the talk. And so this is the notion of destructification. So the talk mostly aimed to show that, okay, changing your foundation can be a helpful thing to understand categorical notions in the right setting. But there's a situation where I have like destructification. So in other words, if I want to impose a certain equivalence type, I have to weaken the categorical structure so that it actually works in the first place. I have no other choice. And so in other words, then I'm using a lot of like the existing categorical literature. I'm using stuff that people have worked out with regard to the coherences you need to actually make this work. And so there's this kind of nice feedback loop between category theory and this kind of defining categories in univalent math that is happening here, that I think is a fun thing to notice. Okay. So the summary then is category structures come with many equivalences. And I can use the identity that I find in univalent foundations to capture those equivalences. And yeah, I don't know. I think this is like I would have hoped that this would kind of be a standard way to think about categories, that instead of just using a classical way and then always adding the equivalence or context, we just like define the notion that we want with the equivalence built in. And that should actually be just the way we think about it. But I don't know if it will happen, but I think that would be kind of like a positive development. I did have 2 slides about formalization and how it's related, but in interest of time, I will end it here. And if you have questions, I'm happy to answer.
Right. Do we have any questions for Nima?
I have a question. Is there a way to go back from univalence to more classical notions, for example, some kind of rectification theorem?
Is there a way to go back from univalence to?
Yeah, that is to say, when a weakened notion is actually equivalent to a stricter notion.
So I think in some sense, I think if I understand the question correctly, one kind of it cannot be said without adding some additional axiom or structure or something. So if I am in if I choose a univalent type theory, then and with some constructors, then I have a notion of identity. And that notion of identity is in some sense the king. Like this determines everything. Like so if 2 things are equal, then they're just equal. And I cannot distinguish between them in any way. So there's something there's nothing such a thing as a stricter notion than what the identity allows. But what I could do is kind of like, okay, add some further structure to the type theory if I want to. So this is somewhat outside of the scope of this talk, I guess, but there's like sort of like 2-level type theories. Maybe that's the direction of what you're asking, where you have 2 layers. And 1 layer is univalent, but there's another like strict layer, and they interact in appropriate ways. And that kind of allows for some kind of strictness in the context of mostly kind of like univalent identities.
See, that's one possible answer. I say, I meant something like Maclane's coherence theorem.
Exactly. That's what I'm saying. Like this is kind of like lost, right? I mean, this is actually it's actually here. So it's funny that you're asking, because in some sense you cannot do anymore the kind of stratification results that we do in classical category theory, because there's just no way to distinguish between the strict one and the non-strict one. It just doesn't mean anything in a type theory.
I see.
Because you have to provide, I mean, like when I'm defining a category, so I didn't define a bicategory as written out, but if we look at where is it? Here. If you look at this, you can, from this definition, you can imagine how a bicategory should be. You should keep going. And you really have to give a witness for every single identity that you know when you define a 2 category. You can add, if you want, some kind of like here you can add some set theory assumption maybe, but you cannot avoid giving any witness. You cannot just like say these are equal and be done. You still have to like specify every time there's this one term in the identity type, and this term has a name, and you cannot like not do this in the type theory setting. And that is precisely why, like, a priori you lose some of these kind of like stratification results, unless, as I said, if you add a further layer, like you need to have two notions of what it means to be equal, and then one needs to be stricter and one needs to be weaker, and then you can say, okay, like I add this second layer and add some stratification results there.
Okay. Thank you.
I have a completely different question. So you said that you kind of use this idea for categorical settings. And like from your example, I kind of see what you mean, but is it even possible to be more precise?
Not yet.
Okay.
I mean, it's a good, but I mean, the question is, what is the boundary example or something? Like, what is the limiting factor?
Right.
I don't know. I'm not. I mean, it's also one problem is also that the literature on this is also somewhat scattered.
Mm-hmm.
Like bi categories and double category, and like in general, like even like in tri categories, even worse.
Mm-hmm.
But yeah, I mean, it's presumably you would imagine that like it holds very broadly. Like I don't see any fundamental limitation for lots of kind of algebraic or kind of like sort of this type of structures, right? Like so these dependent algebraic structures.
Mm-hmm.
But I mean, this thing lacks a more precise formulation. This is also why it's called a maxim, right? But if it was like a more precise name, it would call it some kind of theorem, right? I mean, there's supposed to be a theorem here somewhere that like kind of like makes sense of this. Wait, where is it? Okay, I have to like click through. So there's like right now there's this kind of here. There's this kind of like correspondence, but this correspondence should presumably become some sort of very precise theorem at some point, and then it would like get a better name. But right now it doesn't deserve a better name because it's not yet a theorem.
Mm-hmm. Okay, thanks. I have another question, which is, so it seems to me you're proposing like a different perspective on the way that we consider these structures, right? Like you said something like, instead of looking at a structure and then having as a second thought, what should the equivalences be, to actually think of the equivalences as you build the formalism of your structure, and it's kind of built in.
I mean, I think that we are already doing this implicitly, and I think that is my impression, that usually when you pick up a paper, it might say category theory or true category. I mean, you have written a lot about double categories, and you're very familiar, and you can pick, there's several different papers on double categories, and one will focus on, let's say, horizontal bi-equivalences, and one will focus on gregarious equivalences. Right? Like there's, I don't know, and so on. And there's a clear kind of, like especially in the double category literature, really notice this, that the behavior of the double category, what you pay attention to, changes quite a lot based on the equivalence you care about. So for categories, you don't notice this too much because isomorphism equivalence, there's two choices and they're kind of close. But the more you add a structure, the more choice there is, and it really changes the type of math you kind of do with it. So I think there is some implicit choice that people already make. And what I'm saying is this setting allows you to make it explicit. Like that's I guess the way I think about this.
Okay, I see. So do you have a sense of whether, aside from making it explicit, will you expect that this setting would allow us to understand better the class of equivalences that we chose?
Well, I mean, understand the equivalences better. I mean, this is, I think, somewhat dependent on the context, right? I mean, a priori, let's see. it does help because you kind of relate the equivalence you're looking at to the structure you're constructing, right? So, I guess for categories, even this is kind of clear, right? I don't know. If you think of a univalent category, like if you think of the res nerve, then what you're doing is kind of, you're looking at like the underlying group weights of the various kind of diagram categories. And if you think of the category this way, then it becomes kind of very clear that there's no such thing as an object of a category, I think. Like, I think you intuitively recognize this much better. If you really recognize that the type of objects should be the underlying group weight and not like a set, right? Which is what univalence would, for example, impose on you, right? Or like a completeness condition, so to speak. And I think this is like similar for the higher ones. Like it's the way you define the objects kind of tell you what you can do with them. In a way, like in this setting, and this is the point, right? This is not for fun, right? When they say stuff like here for the category one, when you say stuff like C is equal to D if they're isomorphic, like this is like rigidly imposed on everything, right? So like you literally cannot say something that is not isomorphism invariant. Because like every like in set theory, right? If I want to say something about sets, if I take one set out and plug in an equal set, it has to still be true and has to still hold. Like there's no way to say anything that's not like this. And here's the same. When I say C equals D means the isomorphic, I cannot phrase anything in this language that would not respect isomorphism. Like it's literally impossible. And similarly, when I now work in this, let's say here in the setting of univalent categories, I cannot say anything about this, like this type of univalent categories that does not respect equivalences. And there's just no way to, it wouldn't mean anything, right? So for example, I cannot define, for example, you can try, but you would fail to define such a thing that is trying to like take your univalent category to like its objects or something. Like this does not exist and you couldn't do it.
I see. I have one more question if nobody.
Yes.
Okay, so typically the way that I try to understand equivalences in any setting is through like homotopy theory, right? To like construct some model structure or construct some kind of framework. Is there any interface between this and what you told us about today?
Well, the interface is, this is like, I guess you can think of a model category as a categorical manifestation of these like univalent type theories. And so like in some sense, there's this whole deal about picking the right five-band objects and then characterizing the weak equivalences between the five-band objects. Like I know you in particular have like thought about this a lot, right? In various papers. And you can think of like this, like shifting this effort into the language, into the foundation you use. Right. So, it's not that you can see this already here, right? It's not like you can see this already with this univalence condition. Because what is it? Like the completeness condition kind of was introduced by Charles Rasekh, specifically with the aim of saying these are the five-band objects in a model structure where the Dwyer-Kahn equivalences are precisely the like Reedy equivalences. So you can think of the Reedy equivalence is always kind of like the kind of like equivalence that you, so the equivalency, the Reedy equivalence is kind of like the identity, right? So two things being equal is kind of, if you unwind it appropriately, it's like kind of like the Reedy equivalence. And now you want the equivalences to correspond to the Reedy equivalences. So you ask yourself, what condition should I impose on the objects? So i.e. like a vibrancy condition, so that this actually works out. Like this is not a precise statement, but like this is more or less how you can think about this. And that's how exactly the same conditions show up, right? Like the way that the completeness condition showed up on the kind of model category side, this univalence condition shows up on this kind of type theory side. It's not, in that sense, it's not that different.
Okay, great. Then let's maybe thank Nima again.